Welcome back to our HVAC vacuum series. Today's going to be part 3 of how to measure that. And before we're going to measure vacuum, we need to understand what vacuum is. To understand what vacuum is, we need to understand what pressure is. So I got a quick little demonstration for you. So it's not vacuum that's crushing this can so much as it is the atmospheric air pressure around it that's pushing it against it. And that atmospheric pressure is what we're really measuring, or actually measuring a lack of. So for the atmospheric pressure that we're under is 0 psi gauge, which is typically 14.7 psia, and here in Las Vegas, due to the dry air, it weighs more, and we're usually pretty close to sea level conditions, even though that is 0 inches of mercury, and that's usually 760,000 microns. And water at that temperature will boil at 212 degrees. And one of the big things we need to do with HVAC is not only pull out the nitrogen and the oxygen, but we want to dehydrate. And the only way we can dehydrate is to get that water to boil into a vapor so that we can pull that vapor out. It's difficult, though, getting that system, all that copper piping inside that system to be at 212 degrees. So what we're going to do is we use a vacuum to make that happen. So I have a little demonstration set up for you. Here in my vacuum pump, I have put some water in this chamber down here. And so if we put this into a vacuum, we can see that we can manipulate the boiling point of water, we can manipulate the saturated temperature of water, and we can make water boil even though it's not at 212. So I don't know how clear it'll come out, but we'll give it a shot. You see it boiling. So this is what's happening to the water inside the refrigeration system, except it's not that dramatic. There's hopefully not going to be standing water in there, but any of that water that is on the side walls of the units, water from the moisture in the air, even though it's a dry climate, you're still having moisture everywhere, all inside the unit. That moisture is going to be mixed with the oil, and so as we drop the pressure down, we remove the atmospheric pressure, what we call a vacuum. That's what we're doing, is making that water boil out. Once we boil that water out, we can remove it with our pump and have it clean. And the reason we want to get that water out is because of acid. So what happens is that moisture stays inside the refrigeration system. As we go through the compression cycle, it turns to an acid. This happened even with the aquabenzoline and mineral oils, but it's much more of an issue today with the PE oils that we're using with the 410A and the new refrigerants. Those oils are actually, from what I understand, an acid that's been dehumidified to make a really great oil. So if we get that water back into that, we let water at any time get into that oil, it does turn into a very severe acid, and that acid is going to eat away the windings on the compressor, which is going to be a callback or a warranty issue. It also eats away the copper inside the systems, especially now there's a lot of rifling going on, and that acid gets up in those little grooves and eats the way from the inside out. A lot of coil leaks happening from eating from the inside out due to that acid in the system, and also copper plating. As it starts eating away bits of copper inside that system, that copper finds the hottest part, which is usually on the bearings of that compressor, and the copper attaches itself, it plates the bearings of those compressors, and as the compressor is trying to run, the tolerances get tighter and tighter, and it slows the compressor down and eventually locks it up. So copper plating is also a really big issue with the acid. So it's incredibly, incredibly important that we get that moisture out. Now, I've heard many times, oh, well, I didn't need that before. But with the mineral oil, it was pretty forgiving oil, even though we were supposed to do it then. And I hear all the time people talking about, the ways that we've done it in the past. And so we're just going to review a few of those ways and then move on to some of the other ways that I feel are a much better, more accurate way of checking. So first off, we'll start with what is a micron. And it's just a measurement, just like we use feet and inches, but instead of measuring with inches of mercury, it's much smaller than an inch. There's actually 25,400 microns in 1 inch of mercury. So it's like it'd be like a carpenter trying to build a cabinetry with a yardstick. 25,400 microns in 1 inch. And on a vacuum gauge, on your pressure gauge, your compound gauge, you can't even really see 1 inch on there. It's not calibrated. Even if it was calibrated, you can't see 25,400 microns to know if you're down into the boiling point where that water should be. So here I have a typical Yellow Jacket Ritchie brand, Ritchie series manifold set. This one's for R22, which was a lot easier to see the pressures if you remember. And on this one, if we look, the compound gauge, you can easily see the differences of where it goes pulling that into a vacuum. So it was a lot clearer to see because we had less numbers in the same amount of space. But even at that, they skipped at increments of 2. So between 28 and 30, and the thickness of your needle, you couldn't possibly see that. You're looking at a difference of 50,800 microns. So even if this gauge set was properly calibrated, seeing if you're at 500 microns is just really not going to happen. Let's just be honest. Now we have the new manifold gauge sets that do 410A as well, which is a higher pressure. So with that higher pressure, we have to put more numbers in that same exact area. So now if we can see this, we have our 0, which is quite a wide span. We have 2 marks, and then we have 30. So if we look at that on this drawing, we can see that there's quite a large space there between these numbers. So trying to see how many microns you're at, or if you're even at a good vacuum, is really it's just impossible. So what brings us to, we need to actually measure our vacuum with microns. If we're going to build cabinets, we need to measure with a tape measure that goes down to fractions of an inch. And these microns are going to be our tape measure that measures within fractions of an inch. That way we know we're doing a quality job. We do a quality job, less callbacks, and we know that we're treating the customer right. So, micron gauge, vacuum gauge. I hear all the time people talking about these new micron gauge, but it's really not new. This was my first one, and tell my age a bit, but thermistor vacuum. This is what I had to start out with, and it worked well. It worked really well. Of course, we had to wait for it to warm up. We had to calibrate it. We had to have, most of my adapters are gone now. We had these adapters that we had to install, and I remember all of our recovery tanks used to have these ports actually installed in them. But this was what I started out with. It was a reading vacuum thermal microns and thermistor vacuum gauge. Worked great. Took a little bit of time getting it all calibrated, but it was an analog micron gauge. Luckily, we've improved on that, and now we have digital micron gauges, which work a whole lot better. It's a nice digital number on there. You don't have to wait for them to warm up. The problem is, though, that these do get dirty. A little bit of dirt on there, and it can really throw the sensor off. So it's very important that we use alcohol or some other type of cleaner that your micron gauge recommends, because manufacturers always override anything anybody says. We'll use alcohol in here. I like to put the alcohol in, keep these things clean. I clean my micron gauge after every use. They are very expensive. I don't want to go out replacing them, so I keep these cleaned up. I want to make sure I keep oil out of my micron gauge. I don't apply pressure on it. I want to keep these lasting a long time, keep spare batteries, and make sure these things are going to last me a long time. So talking about the micron gauges, there's several ways. Some of the manifold gauge sets that we see now have micron gauges built into them, which is a really nice feature. These are my sets, and it's really nice as it pulls down. It shows the inches of mercury. Once it gets down to 1,000 microns, it starts reading that microns. The problem is that sensor is here in my manifolds, and it's asking for trouble getting clogged up with dirt. I really take good care of these. I keep them cleaned out, make sure I keep that sensor clean. But what I'm really worried about with this is it's so far from my unit. It's closer to my pump than it is to my unit. My micron gauge being here and not actually telling me what's happening in that system. So what I prefer to do is when I have my valve cores out and I'm pulling a vacuum with this being my hose, this side port, I like to take that Schrader port out and I install my micron gauge directly on the suction side of that side Schrader port. So now as I'm pulling a vacuum through the back side of this valve core removal, I'm reading my microns directly on my unit, right there close to the suction side. I know what's happening inside my unit. As my pump's pulling down a deep vacuum, any restriction along the way is going to give me a false reading. So the farther away that my vacuum gauge is from my pump, the better off and the more accurate I'm going to be at what's happening inside that system. So this is where I like to do it, and I like to have these brass tubes or steel tubes, something other than just simply the rubber, because I want to make sure I'm not leaking through this tube. This way, when I do a pressure test, a vacuum standing pressure test, and I close off my valve, there's no way it's pulling through any of those tubes, and it gives me a much more accurate reading. A lot of people complain that a few things. One thing they complain about is they can't get down to the microns. And there's a few reasons for that. One is usually we're pulling through the restrictions like we talked last time. But some micron gauges, they only have a single sensor in them. And that single sensor won't start reading until you get down to, say, 1,000 microns or 2,000 microns before it even starts reading. So you'll see OL, or atmospheric conditions, at a much higher pressure. So it takes a while before your micron gauge ever starts reading. Usually if your micron gauge isn't reading, you're not boiling any of that moisture out. Other micron gauges, this particular one, it actually has 2 sensors in it. So it's reading atmospheric pressure right now, being 704,000 microns due to our current atmospheric conditions. And as it pulls down, my second sensor that's in this will take over. What I do like about it is when I shut this off, when I get down to my numbers that I want, I shut this off, and these numbers are going to go up. How fast they go up would depend on 2 things. One of those things being how much moisture is left in that system. If I have a lot of moisture in that system, that moisture is going to still be boiling, and this boiling, it's increasing the vapor pressure. As that vapor pressure goes up, I'm going to start reading that in my microns. Usually it'll go up to a point and level out. That's how you know you have moisture. If it continuously goes up and does not stop, usually means you have a leak. And it's using a vacuum to find a leak is not recommended, but you do know for sure that you have a leak in that system. So I like to shut mine off, make sure it's not rising above, make sure that all that moisture is boiled out of that system. I want to make sure it's pure and dehydrated. With this, it's a Bluetooth style, and with that one I can monitor this with my phone. I can see my degradation of vacuum. I can make sure that I'm free of moisture. I stay below that 500 micron mark. My goal is not to get to 500 microns. I want to be below 500 microns to make sure I've boiled all that moisture out of the system. The next thing is, how low can you go? And I've heard a few different scenarios on this, but from what I've generally picked up from most manufacturers is 200 is enough. Some manufacturers use an additive in the oil. And at 200 microns, your oil is not going to boil away, but under 200 microns, some of the additives can vaporize and be pulled out. And if you take the additives that the manufacturer put in, if you pull those additives out, you're changing how they've designed that system. So I don't recommend that. So I usually try to stay above 200 microns, but I want to make sure that if after I'm isolated, after I've given it time, 20 minutes preferably to isolate, I want to make sure I never rise above 500 microns. If I, after having that unit shut off, never go above 500 microns, I know that there is no moisture in that system. Moisture is going to kill it. I want to make sure I'm moisture-free. Those are some of the ways I do to take care of vacuum. Make sure that I know that I'm doing the right job. I want to know for a fact that that system is moisture-free. I don't want any acids in that system caused by anything that I did. One of the nice benefits here is our lower humidity. Usually makes our vacuum system a little easier as long as we don't have those restrictions in it. But whichever method you prefer, please recommend using a micron gauge, knowing that you're in that boiling point, knowing you're boiling that moisture out of that system. So I hope that helped. If you have any questions, please let me know. Thanks.